So you clicked on this video because you wanted to learn more about neural networks, the technology driving the AI revolution that we're currently living through. But what if I told you that you already know what neural networks are? It turns out that a neural network is nothing more than a function, just a regular mathematical function, the same type of function you've been using since grade school, where you hand the function some input x and it produces some output y. In essence, neural networks are just input-output machines. While in practice these inputs might be complex, multidimensional vectors, we can go ahead and begin with a simple example to help us understand how they work. Let's say that we want to build a neural network that can predict house prices. For this example, let's say that we have access to a dataset containing house size, measured in square feet, along with house prices, of 8 recently sold homes within a neighborhood. Let's go ahead and visualize this dataset by putting it on a graph. Each data point here represents a single house, where we can observe the house's size and its sale price. Our goal here is to be able to accurately predict the price of a new house not a part of our dataset, given its size. Remember, neural networks are just input-output machines, so it's going to help to visualize this in terms of inputs and outputs. In this case, the input to the neural network would be the size of a house, which we'll call x. This feeds into a node, also known as a neuron, where some function is applied to it, and then outputs its prediction for the price of the house, which we'll call y. The magic happens inside of this neuron, where we must fit some type of function to the dataset. Because this example is so simple, we can fit a function to this data quite easily with something called a linear regression, where we just fit a straight line to our data. You probably worked with linear regressions a lot throughout grade school. Recall that the equation of a straight line can be expressed as y equals mx plus b. While this is not exactly a neural network, you can think of it as being the simplest form of a neural network. All this neuron does is implements this linear function that we fit to our dataset. If we now want to use this neural network to predict the price of, let's say, a 2,000 square foot house, we would simply hand it an input value x of 2,000. The neuron would sub this value into the linear function, evaluate the equation, and then output its prediction for the house price, which we'll call y. So, what we have here is an example of a neural network with a single neuron. You might imagine that a more complex neural network is formed by stacking many of these single neurons together. Let's visualize an example where we add an additional layer of neurons. Rather than using house size as the only input variable, what if our dataset came with other input variables as well? By the way, we call these input variables features. Maybe in addition to the house size, we have access to the number of bedrooms. While the price of a house is definitely dependent on its size and its number of bedrooms in isolation, maybe the real underlying driver of house price is what size of family it can support, which can be inferred from both the house size and the number of bedrooms. We can actually feed both of these features into a single neuron to get an idea of family size. Let's say that we also have access to more features, such as the zip code and the average neighborhood income. Of course, these features would impact the price of a house on their own. However, maybe what really matters to the house price is the commuting distance to the downtown core, which can be derived from the zip code. Maybe the quality of the schools in the neighborhood also impacts the price, which can be inferred from both the zip code and the average neighborhood income. At this point, the idea is that people use these more important, underlying factors that really matter to them to decide how much to spend on a house. Since these factors might seem to determine housing prices more accurately than the raw features in our dataset, we can feed all of these into a final neuron that we can use to predict housing prices more accurately. At this point, we now have an example of a larger neural network, which is more realistic to something you might see in the real world. We still hand it raw input features from our dataset, which are x values, and it still outputs a predicted house price, which is our y value. The entire neural network is still just an input-output machine, just a little more complex now. Each individual neuron within the network is still just a linear mathematical function, just as we saw in the previous example. The magic of neural networks is that we only need to give it an input value x and an output value y for some data within a dataset. All of the values in the middle, which are important contributing factors, are figured out by the neural network itself during training. Let's take a look at the architecture of such a network more generally. This is what this neural network might look like if it was implemented in the real world. What you might notice here is that every single input feature is connected to every single node. In other words, every single node is fed all 4 features from our dataset. We don't need to pick and choose which nodes are supplied with what data. This type of architecture, which is very common, is known as a fully connected neural network, or FCNN for short. The beauty of neural networks is that as humans, we do not need to decide that this node represents the family size, and that this node represents the commute distance, so on and so forth. That would very quickly become infeasible when dealing with millions of features and nodes. Instead, we supply every single node with all of the features, and the neural network will decide on its own what it wants each node to be. If it spots that a given feature is good at making the prediction more accurate, it will learn to include it, and if it learns that a given feature is not necessary, it will shrink its weight down to 0. The remarkable thing about neural networks is that given enough data and training examples, they can learn virtually any function, no matter how complex, that can accurately map from inputs to outputs. They're powerful and flexible tools that can learn to represent even the most complex patterns in data. Let's give some context to what we covered so far. Neural networks are structured in layers. The X values are referred to as the network's input layer. The final layer that outputs the Y value is referred to as the output layer. Any layers in the middle of the neural network are referred to as hidden layers. In this example, we only have a single hidden layer. This type of neural network with a single hidden layer is referred to as a shallow neural network. In practice, neural networks will have multiple hidden layers, as we can see here. These types of neural networks are referred to as deep neural networks. This is where the term deep learning comes from, which refers to the process of training a deep neural network. In our first example of a linear regression, you can actually think of this as a 0 hidden layer neural network, as the input layer connects directly to the output layer. So far, I told you that each node in a neural network contains a linear function. Just as we were taught in grade school, the equation of a line can be expressed as y equals mx plus b, meaning that the value that each node computes and feeds forward into the next layer is equal to mx plus b. When it comes to neural networks, we use slightly different conventions, since most of the time, all of these values are multi-dimensional vectors rather than individual numbers, which we're just using to make things easier to understand in this video. The m value, which is normally the slope of a line, we instead call the weight, which is represented with a w. The weight controls how much influence the input value has. The b value, which is normally called the y-intercept, we instead call the bias. The bias allows adjustments to be made to the output independently of the input data. Just as an aside, you may have noticed that we have 4 different x values in this example. This means that rather than being a single real number, x is a vector containing x1 through x4. Similarly, w is also a vector of the same size containing 4 different weights. If we expand out the equation of our node, we can see that each underlying x value gets multiplied with an individual weight before adding in the bias. We'll be keeping the equation in this condensed form for now, but it is an important detail to note. In summary, each node is fed an x value as input, which it multiplies with a weight and then adds a bias to. The result of this calculation is then fed forward into the next layer of the network. These weights and biases are referred to as the parameters of the neural network. You know how you're always hearing about how the newest AI model has hundreds of billions of parameters? That just refers to the number of weight and bias values that are contained within all of the nodes across the entire neural network. This is where the so-called knowledge of the network lives. Throughout this video, I didn't make a clear distinction yet between what a neural network is and how they are trained. Building a neural network is only half the battle. Once you build your network, deciding on how many layers you want and how many nodes you want within each layer, you then need to train it on some data set in order for it to learn anything useful. The learning process is where these weights and biases are determined. How a neural network learns is a massive topic that definitely warrants its own video, however I'll go over a simplified example in just a second. Before that, there is one last, very important component of neural networks that I left out. If you've been paying attention, you might have noticed quite a serious problem. Let's go back to our first example of a linear regression that predicts house prices. If we view a little more of our linear model, you'll notice that it's actually possible for our model to predict negative house prices. Of course, this shouldn't be the case. To fix this, we can modify our function to have a minimum value of 0 to prevent housing prices from becoming negative. It turns out that this kind of broken, nonlinear function is very common within the field of deep learning, and it's called a rectified linear unit, or ReLU for short, which restricts output from becoming negative. If we want to see what this would look like mathematically within our node, we would first still apply the same linear function that we did originally, and then we would hand this to a ReLU function afterward before evaluating the final result, which will now have a minimum value of 0. It's important to note that this node now has 2 distinct calculations to make instead of just one. This practice, where a neuron applies a linear function at first, and then applies a non-linear function afterward, is the final key concept that we were missing. These non-linear functions are known as activation functions. Basically, after each neuron applies a linear function to its input, it hands the result to a non-linear activation function, which is referred to as the neuron activating, also referred to as the neuron firing. These nonlinear activation functions are crucial within neural networks, as without them, even deep neural networks would be limited to solving only simple, linearly separable problems, behaving like a linear regression model. Nonlinearities are what enables neural networks to learn and represent complex patterns in data. The true power of neural networks is seen when we apply these nonlinear activation functions to all of the nodes within a larger network, rather than just to a single node. We can visualize the importance of activation functions quite nicely in a 2-dimensional space. Let's say that we have a dataset of blue and orange data points, and we want to train a neural network to be able to classify which color a new data point should belong to. Let's use this data to train a neural network with no activation functions versus a neural network with activation functions. In this case, since our data is linearly separable, both networks are able to learn a reasonable decision boundary. Now, let's see what happens if we use a more complex dataset, which is more representative of something that we might see in the real world. As we can see here, it is clear that the strictly linear neural network is unable to model this data, as it is essentially only capable of drawing a straight line. On the other hand, the neural network with nonlinear activation functions is able to represent this data quite easily, as it can draw a decision boundary of virtually any shape. This is just a 2-dimensional example to make things easier to visualize, but the same principles apply even when dealing with hundreds of thousands or millions of dimensions. At this point, let's recap what we covered so far. We know what a linear regression model is, a zero hidden layer, strictly linear neural network. Next, as we build up our understanding of neural networks, let's take a look at a slightly more complex model known as a logistic regression. This is going to be very similar to a linear regression, but with one of these nonlinear activation functions applied to it. A logistic regression can be thought of as an intermediate stepping stone before getting a little more complex to shallow neural networks, and then going all the way to deep neural networks. Logistic regressions are often used for binary classification. Binary classification is when a model has a binary output, being either a 0 or a 1. Let's take the classic example of a binary classifier for cat photos. Let's say that we want to feed a model an image, and we want it to output a 0 if the photo is not a cat, or a 1 if the photo is a cat. Seems simple enough. Images can be represented as a 3-dimensional vector, where we have the number of pixels along the x and y axis spanning 3 color channels deep. We can unroll this 3-dimensional vector into something called a feature vector, which lists each of these values in a large list. This feature vector is our input value x in this case. A logistic regression is also a zero hidden layer network, meaning that our input layer feeds directly into our output layer. Just like with a linear regression, our node takes in our input value x, where it will apply weights to each underlying value, and adds in a bias term, before outputting some number that unfortunately in this case could be negative or much larger than 1. Once again, a linear model does not suffice for our network to work as a binary classifier. In order to restrict our output to be in between 0 and 1, we can apply another type of activation function known as a sigmoid function, which looks like this. Its output values range from 0 to 1, with 0.5 right in the middle, which seems to fit our use case perfectly. Essentially, a sigmoid function takes in any real number as input and squishes it down into the range between 0 and 1. Just as before, we hand the output of our linear function into this nonlinear sigmoid function, and we get numbers in between 0 and 1 as our output, with the decimal values in between acting as our model's confidence in its prediction. This type of model, with 0 hidden layers and a sigmoid activation function, is known as a logistic regression. This is essentially the building block of neural networks. Once you add in a single layer, you've got a shallow neural network, and once you add in multiple hidden layers, you've got a deep neural network. These deeper networks can employ multiple different activation functions, even within the same network. Hopefully you're now starting to see that neural networks aren't so intimidating after all. Now, lastly, I mentioned that building a neural network is only half the battle. Once you build a neural network, you need to train it on some data set in order for it to learn anything useful. I'll explain how the training process works briefly, however this is a large topic, and it definitely deserves its own dedicated video. Basically, during training, you hand the neural network some input data from your dataset, and the first layer of nodes will apply their weights and biases a part of their linear function, apply the nonlinear activation function, and then feed this value as input into the next layer of nodes. This process repeats, layer after layer, until the end, where a final output is computed. This process is called forward propagation. Once forward prop is complete, the final output is referred to as y hat, which is the predicted value. We compare the model's output, which we know is called y hat, to the real value of y, known as the ground truth value, which we can observe from the dataset. We use a special function called a loss function to compare how far off the network's prediction was from the ground truth value. In a perfect world, if our model was 100% accurate, y hat would be equal to y. But in practice, there will be a difference between them, which is referred to as loss. Once the loss is calculated, the network begins a process known as backpropagation, where it now takes what it just learned from the loss calculation and begins using it to incrementally update each node's parameters. Every time these parameters are updated, you can think of this as the neural network learning from the data that it was fed. The algorithm that it uses to know what adjustments should be made to each and every parameter within every single node in the entire network is known as gradient descent, which is truly just an elegant and beautiful algorithm grounded in calculus that definitely deserves its own dedicated video. Once backprop is complete, we now repeat this over and over again for all of the examples within our training set. Once the neural network is finished with its training, and we're just using it for real-world, everyday, regular use, the only process that needs to happen is forward propagation in order to get our desired output. As we've seen, deep learning is a broad field, encapsulating elements from computer science, mathematics, and data science. If you found this video interesting, and you want to keep on exploring similar topics, look no further than this video's sponsor, Brilliant. With Brilliant, you learn by doing, engaging with thousands of interactive lessons in math, data science, programming, and AI. Take for instance their course on neural networks, where you get to see some of the concepts covered in this video in action. Here's the inner workings of a shallow neural network that has been trained on handwritten digits, being able to classify what digit you drew in real time. They also have a course on large language models, where you get to learn and interact with a different kind of neural network designed for generating human-like text. One of my favorite parts is their large catalog of math and data courses, which serve to give you a proper foundation, filling in any knowledge gaps you might have, while also keeping learning interesting, fresh, and relevant. The best part, Brilliant makes it easy to turn learning into a daily habit. They provide their lessons in manageable, bite-sized pieces that can be done at any time, helping you build real-world knowledge in just minutes a day. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/DanielBachter or scan the QR code on screen. Or you can click the link in the description. You'll also get 20% off an annual premium subscription. Of course, the field of deep learning is absolutely massive, and this video is just barely scratching the surface. This is by no means a comprehensive overview of neural networks, but is rather just meant to get your toes wet. Just as we have built up from linear regression to logistic regression to shallow and deep networks, we can keep on going. The most basic type of neural network that we covered in this video can be referred to as feed-forward neural networks. There are many different types of neural networks as well, such as convolutional neural networks, recurrent neural networks, graph neural networks, and more, which I might make videos on in the future if you find this to be an interesting topic. If you've made it this far, you might be interested in checking out some of my other content. Thanks for watching.